Greetings. In this series, we are going to look at mathematics from around the world. Math is a subject that is studied around the world by various peoples and has involvement in culture at various levels. We have images used as artwork from geometry, and we have geometries that were studied because someone was looking for one thing, discovered another, and then that was applied to something else. In this series, we want to look at mathematics from around the world and the various things that connect us as a people in a beautiful creation. I hope you enjoy worldwide mathematics. Greetings, math friends. In this episode, we are focusing on Israel, and we are looking at the Three Radii Theorem. Now, the interesting thing about this theorem is that it was essentially just discovered in 2016. A high school student was trying to do her work, and as many students do, they presented an attempt at a solution to their teacher. Their teacher told them that they had to prove something if they were going to use it. And what ended up happening is that the thing that was presented wasn't in the textbook. And the student, working with her father on her own time, was able to come up with a proof for this. And that's an amazing thing. It always interests me when people within the last 100 years or even the last 50 years, come up with a new theorem in plane geometry. It seems like with all the time that plane geometry has been around, we probably would have found all the ins and outs, and yet we're still making new discoveries. And this 16-year-old girl did just that for her class. The article that I found talks about a little bit about her school and her extracurricular activities. It gives the statement of the theorem, but it does not show her proof method. And I could not find her proof method, so I'm going to present a proof for the Three Radii Theorem. I don't know if it uses the concepts that she used in her proof, but I feel like I have a pretty good idea of proving this theorem. This is the Three Radii Theorem that was produced in 2016 by the 16-year-old Tamar Barabi. I didn't clean up the language on the theorem. I think it could be tightened up, but I used the original language that was in the article that I found. The first thing that we're going to do is we are going to choose a point interior to the circle that is not the center of the circle. So, without loss of generality, we're just going to choose some point in here, not the circle. And then we're going to extend from it line segments that intersect with the circle itself. And then we're further going to state that the way that we've constructed this, all three of these segments are congruent. So this is our diagram at this point. We have a point somewhere in the circle. Extended from it are three congruent segments that intersect the circle. So this fulfills the first part of it. Now, it's up to us to prove that this point P that I've randomly chosen was in fact the center of the circle. And to do that, I'm going to create what I know to be the radii of the circle. I'm going to connect the center to two of these points, and I'm going to label these A, B, and D. I'm not using C here because I chose to call the center of my circle C. So this being a radius is going to be congruent to this, which is a radius. So I have this triangle, I have this triangle that's in red, and this triangle over here. I'm going to create one more triangle. I'm going to connect the center to this third point over here. And I'm also going to connect A and B here. So let's real quickly take a look at this. The reason I can create segments between points is because in plane geometry, any 2 points lie on a line. So you can create these segments because they are a piece of a line. So this is how we're going to start with this. And also, to do this proof, I'm going to do it by way of contradiction. By way of contradiction, we are going to assume that P is not C, that this random point that I've chosen is not the center of the circle, and our argument is going to go from here. So I have this setup that I've created, and I want to pull this one particular triangle out to the side and look at it in more detail, and then we're going to reinsert it into the circle, discuss as my argument progresses. So I'm going to pull out this triangle. Once we've pulled these triangles off, we want to look at these triangles and their properties. So we have 2 isosceles triangles. We have the big triangle BCA, and then we have the smaller triangle BPA. And we know that these triangles can't be similar to each other because they share a side, but their other side lengths are not the same. We know they're not congruent because we don't have congruent parts. We do know from being the isosceles triangles that this angle CBA should be congruent to CAB, and that angle PBA is congruent to PAB. What I want to do is I want to construct the perpendicular bisector of BCA. We can do this because the perpendicular postulate in Euclidean geometry tells us that given a line and a point not on the line, there is a unique perpendicular passing through the line orthogonally and passing through that point. And so we're going to create that. So I'm going to bisect segment BA with the perpendicular bisector, and it's going to pass through C. So that means that from B to this line is congruent to the section that's from this line to A. All right, this is the fun part. So we have this perpendicular bisector in here. It's bisecting the line segment BA, and it passes through point C. Now, the smaller triangle is sharing that same side, which means that this side is bisected for it as well, and the perpendicular bisector should run through point P. Now, in the way that I've drawn my diagram, it does not. And that's a problem, because according to the perpendicular bisector theorem, if this is the perpendicular bisector, then BP and PA should be congruent, which they are in my diagram, but point P also must lie on that perpendicular bisector, which it does not. And so we've reached a contradiction. That's good for us because that is a step in the right direction. So we have a contradiction here. This triangle was not special. If we would have started with triangle DCB, we can, in a similar argument, argue something similar, and this one's even more off-center than this one. If you look at this triangle, I have that DCB is here, but then DPB is very skewed out here. And so when we go to put in our perpendicular bisector here, this point P is even further off of this triangle. And so we've reached a contradiction with this triangle as well. Since we've reached a contradiction, we know that our assumption was not correct. We assume that P was not congruent to C, but the opposite must be true, that P must be congruent to C. And so, if you have a point interior to a circle, even if you haven't identified it as the center, and you connect 3 or more congruent segments from that point out to the circumference of the circle, and they're all congruent, then you must have found the center of the circle. But I'm not done yet. It's great that we've reached these contradictions. I'm making use of all 3 of the red segments that I originally started with, my random point with these congruent segments put in here. I want to go back to the circle now, and I want to redraw my perpendicular bisectors in the circle. Having these perpendicular bisectors in the circle, remember we pulled this triangle out for convenience to look at it, but it's really living inside the circle. And as you look at the perpendicular bisectors in the circle, they actually have a point of intersection. And guess what that point of intersection is? The center of the circle. And if you look at my diagram, for P to be on this first perpendicular bisector, we need to move it slightly to the left here. And then if P also has to live on the perpendicular bisector here, which is this one here, the only place that P can live on both these perpendicular bisectors at the same time is if they are the center of the circle. And this shouldn't come as too much of a surprise to us, because if we look at one more theorem, we see that if we have a triangle and we put in perpendicular bisectors, they have a point of concurrency called the circumcenter. And if you put your compass point on the circumcenter, open it up to one of the vertices of the triangle and create a circle, you will find that that circle passes through all 3 vertices, and the center of the circle is that circumcenter point. That's essentially what we have here. So where's the triangle? Well, the triangle is if you connect D to B along this section, which was the base of this triangle, B to A, which was the base of this triangle, and then connect D to A, that is the triangle that gives us this as a circumcenter. And that circumcenter creates this circle if you use the distance from the center to any of the vertices of that triangle. And so there you have it. We have demonstrated that this young lady's theorem is not simply a conjecture, not simply wishful thinking on a student's part, but an actual provable theorem. And this is really exciting. I see students try to use ideas in their proofs, and a lot of times the ideas show up in their textbooks and they just haven't written those steps out, or they haven't shown the steps for the proof. But this is a fantastic discovery that this girl had an idea of something that she wanted to demonstrate. It wasn't in her textbook, and she was able to go home and provide a proof for this. Excellent work for the teacher for encouraging this young girl. Even more special This girl had the insight and the drive to discover this new idea and to prove it. So, congratulations to her. Hopefully you have enjoyed this look at a theorem that came from an Israeli young lady. Cheerful Calculations.